All right, ladies and gentlemen, going into Unit 6 of Thermochemistry, and we will continue our talking about energy, how it is changed and how it moves and is transferred. The SI unit for energy is the joule and not the bling bling kind. It is the capital J. An older, non-traditional one, sometimes a very commonly used, is the calorie. Now, this is different than the calories that you would see on the back of a package of your Doritos or candy or whatever it is. And those are actually a little bit different. Those calories are actually a capital C calorie, which is the equivalent, and as we'll talk about this further, but it works here, to the equivalent of a kilocalorie, and that would be 1,000 times more than a small calorie. But the joule in itself, why does the equivalent of it have use mass and meters squared and seconds squared, is because of the namesake that it came from, and that is James Joule. James Joule was a brewmaster and had access to very accurate thermometers, and that's why the importance of him being a brewmaster is there. Is kind of like why he did the sciences. Well, he had access to the equipment, and with that, he was able to measure very small changes in temperature. Now, what he wanted to say or show was that movement had a connection to temperature going up, or energy, and that is what we look at. And so what he did is he set up a system of pulleys that when an object dropped over a certain distance, paddles inside the water would be moved and therefore move the water. And this moving of the water increased the temperature to indicate that there was a connection between energy and temperature. And so that is why we have the joule as the namesake for energy. And so we will use joules, and we will also use the other part of it, and that is the kilojoule, which would be 1,000 times bigger. But those are some of the big important things as we move forward. A lot of it is very, as we use, there is a conversion between the calorie and the joule as well. That will become something that we use quite frequently and almost becomes second nature to us. As we said, is the calorie was originally defined as the amount of heat required to raise 1 gram of water by 1 degree Celsius. And like I said before, the kilocalorie is the with the kilocalorie such as that, or a lot of more commonly referred to as just the capital C calorie that you would see on the back of your there. And that's actually why a lot of times in our health classes, they talk about calories. You need a certain amount of calorie content to maintain energy. And that's because the energy that you get from foods as calories can be done there. Now, anyone who's ever had to do weight loss, they always say, oh, I don't like to count calories. Well, ultimately, that's what it comes down to, an energy balance. And our wrestlers would understand this just as much as everybody else, is that you need to burn more calories than you take in. And so that becomes the thing, is why do some people struggle with that, is some of the how many calories they are taking in as opposed to how many calories they're burning. And so there is a little bit of that. There are certain times in our development that we just naturally, because of how we are growing, we are going through adolescence, that you burn more calories usually than others at that time, and therefore that's why you're like, oh, you just have a high metabolism. Well, actually, what some of that does is that they are actually need more energy, and so they actually start feeding more. as you age, you need to have less and less calories, and that's why if you look on the back, a lot of these are for 2,000 calorie diet, and even some people don't need even less than 2,000 calories. That's just to even potentially maintain. And if you have a sedentary lifestyle, your calorie count could be in the 1,000 to 1,500, and that might be as all you need, depending again on your lifestyle. If the more active you are, the little bit more, but also the older you are, the less you need for that. The calorie is also kind of like why we have that is because of some other things, and we'll look at that a little bit further on. But some of that, all these connections to food and energy, they are there, and so that's why it's a balancing act for many people. So energy, as we talked about, can be converted from one type to another. Now, you can have a high potential energy, which would be like the food that you eat. The energy is stored in chemical bonds. As you burn, as it is digested, it is broken down into more usable energy, such as ATP and ADP, and therefore your body can utilize that at the cellular level. And that's why certain foods, they call them, are very empty calories, is because your body burns them so fast that they actually don't get any good sustained energy from them in that. And so we need to make sure that we're maintaining items that have that good potential energy to kinetic energy. And this happens not just with food, but also with, say, like use of, what's a better fuel, methane or propane or cellulose. Now, cellulose, the more carbons you have, the more potential energy that is stored in those bonds. Now, methane only has 4 bonds with it, and therefore does not burn to the same heat that, say, maybe propane does. And so there's a little bit of those types of things that it's because in propane burns hotter, but it might not be cost effective to use that as a fuel, as the only fuel source. And so it becomes a balancing act of which one works better. And so we have to do a lot of that. It's not just a balancing act for energy that we're eating, but also balancing act for energy that we're using for our everyday life. Now, here is the law of conservation of energy. So the law of conservation of energy, and that is the energy cannot be created nor destroyed. We have a few rules in chemistry, and those are the law of conservation of mass and the law of conservation of energy. Now, obviously, when we look at the law of conservation of mass and law of conservation of energy, there are some exceptions because those nuclear reactions can go in vice versa. But this was an understanding, and we knew that either energy couldn't be created or destroyed. It only transfers through. And so it's either surroundings to the system or the surroundings. Now, it's these types of things that, like, Antoine Lavoisier knew. And so they actually thought, Antoine Lavoisier and others thought that cold was an actual thing, and that it wasn't actually that it was energy was being transferred. And so it was very interesting. That's actually, they thought it was this being of caloric. It was a very interesting thing. And there's a book out there actually for like the history, of thermodynamics, and it's the Conquest for Cold, the Race to Absolute Zero. And so we have some of those things that we need, and it in there kind of talks about this idea of caloric as a sense of like matter, something that could be measured. and it actually, what they were looking at was actually energy. And so that's what James Joule kind of debunked, in that caloric was an actual measurable physical thing, such as mass. Instead, it was just energy that they were measuring with that. And so, even though Antoine Lavoisier, the father of of chemistry, gives us the law of conservation of matter, that wasn't always true. And that's when I think, when we look at some of these greats of science, they all have their flaws, and they have these thoughts that maybe didn't pan out, or they're like, why don't we ever worry about, the flaws of Einstein, the flaws of Lavoisier, the flaws, because they're scientists. They're inquiring about things that, yes, they might not work, or are measurable, but they work through it. And I think that's the beauty of science, is that we have these things. And so the law of conservation of energy truly isn't ultimately there, and that we have the energy can't be created or destroyed, because E equals mc squared says that energy comes from matter, and energy can become matter, and it's very complicated stuff with that. And so, but non-nuclear systems is really what we're looking at, and that's what we want to look at, is that the universe does tell us that the energy lost by a system goes to the surroundings, and vice versa with that. And I think those are some things that we really need to do, and that's what we'll focus on moving forward, is where is the energy moving. So when it comes to that, is that we have this internal energy, a certain energy of the system. You have a certain amount of energy in the system. Now, sometimes that might be a loss of energy by the system to the surroundings, and you have to give forth a lot of energy to do something, and therefore it might require more work on your part. Whereas sometimes to get you out of bed, sometimes it might require more of the surroundings to get you to move, and therefore they are putting a lot of energy into the system, and you being the system, to get you to move. Sometimes it's easy for you, and that loss of energy that it took for you to get out of bed is easy for you, and sometimes those reactions are very easy to do, and but your surroundings are better off. I mean, that energy that you bring to the table is always there, and you'll eventually you get it back. And that's the beauty kind of utilizing some of these examples, is that we find that there is a connection between us giving some of our energy, our positive energy, to others. Usually you will receive that same positive energy, that good flow state, back to us. And so that does happen. Now, sometimes, yeah, some people are just, that won't take that positive energy, and you never get it back. But you in itself will be benefited from it. And so it's kind of that same thing, is that this whole state is of energy that we have, kind of working back and forth. But we're going to look more at the energy that chemical reactions have, and where is that moving to. But we're kind of just utilizing this analogy. So when we look at this, is that there is a change in energy, and if there is a change in energy of a system, it can be positive or negative depending on what's happening. Now, if the reactants, as we see here, hydrogen and oxygen, they give off a lot of energy for water. And now what happens is that the final minus the initial is your basic connection for that, is the connection between what is the change, and that's what your delta is your change, and that is always your final minus your initial. Always what you end with minus what you start with to find it. Sometimes it can be negative. Your delta E, it can be positive or negative. And so it can be either or. So we just need to know. Now, those of you that have sat in the classroom in the first couple of rows have experienced, and most of you that were even in the classroom have experienced the hydrogen balloon. And what we have there is we have hydrogen contained in a balloon, and that when it is exposed to the oxygen through the popping of it of a flame, there is a large amount of heat, energy given off in that, and you feel that energy being released by it. And all we're making is water from that. And so that is why these are set up this way, is at the final, and it's very hard to go from the energy that is contained within water to here. And actually it takes energy to do this. You have to put energy into the system to go backwards. This requires energy. It requires our E. It requires our energy to do this, and that's why, because you have to put energy into the system to go from a low energy state to an upper energy state. The other way, this is almost spontaneous, and it will happen very easily, as we have seen in the classroom. And so we can get water to separate into its elements, hydrogen and oxygen, and that's usually through using electricity and kind of separating out the water with that. And so it can be done. It just takes a little bit more. What this leads us to is the understanding of what two terms that are very important to us. And so we almost want to make sure that we highlight these two terms, and that is an endergonic. Energy is entering the system. Okay, so that's an endergonic. It absorbs, entering the system. That would be, again, energy enters the system. Okay, whereas a exergonic reaction, energy is released, and here we have a little bit different in that energy is exits, and it's the exit part of it. And so energy enters for endergonic and exits for exergonic. And so we can utilize these word associations of exergonic and endergonic to help us understand what is happening within our system as we look at that. And so these are two very important terms that we look at and need to look at it, and we will utilize in our discussion and talking in our labs of what's happening to the system. Is it absorbing and energy is entering, or is it energy being released and energy exiting the system? And again, we're always talking about the system and where that energy is happening. If we talk about the surroundings, things can be very confusing, but it's what's happening to the system and the energy. Is it gaining or losing? And so that's where wrapping our heads around these types of things can be very important to us. We will continue on our topic of internal energy in part 2 of this, as we can continue to kind of get some of these big terminology things taken care of.